Look up at the night sky on a clear evening away from city lights, and you will see roughly 2,000 stars scattered across the darkness. It feels like a fair sample of what is out there. It is not. About 1 in 3 of those visible points of light are giant stars, enormous swollen suns nearing the ends of their lives. Yet giant stars make up less than 1% of all the stars in the galaxy. Something is badly skewing what we are able to see. And understanding that skew turns out to be the key to one of the strangest and most under-discussed ideas about how humanity might one day detect intelligent life beyond Earth. The skew has a name. Astronomers call it Malmquist bias, after the Swedish astronomer who first described it in the 1920s. The idea is simple once you see it. Brighter objects can be seen from much farther away than dim ones. A giant star pumping out thousands of times more light than an ordinary star like the Sun remains visible across thousands of light years, while a small, faint, ordinary star like our nearest stellar neighbor is invisible to the naked eye even though it sits right next door. Cosmically speaking, Proxima Centauri, at a mere 4 light-years away, cannot be seen without a telescope. Meanwhile, Deneb, a blue-white supergiant in the constellation Cygnus, blazes into visibility from roughly 2,000 light-years away. The night sky is not showing us a representative slice of the galaxy's stellar population. It is showing us the loudest, brightest outliers, wildly overrepresented simply because they scream across greater distances. This single principle that the objects easiest to detect are frequently the rarest and most extreme members of their category rather than the typical ones, shows up again and again throughout the history of astronomy, and once you start looking for it, you start to wonder whether the exact same bias might apply to something far stranger than stars. The search for other intelligent civilizations. If alien societies exist scattered across the galaxy, what kind would we actually notice first? Is it the calm, sustainable, long-lived civilizations that quietly endure for millions of years? Or is it something louder, messier, and far more temporary? To understand why this question matters, it helps to walk through a few more examples of detection bias in astronomy, because they set up a pattern that becomes almost impossible to ignore. Consider the hunt for planets orbiting other stars. Long before the first exoplanet was ever confirmed, astronomers had strong theoretical expectations about what such worlds should look like. The template they reached for was the solar system itself: small rocky planets close to the Sun and large gas giants farther out, in the cold outer darkness where ices can survive and where enough raw material accumulates to build a Jupiter or a Saturn. Following this logic, teams around the world in the 1980s and early 1990s built instruments designed to catch the faint gravitational wobble a distant Jupiter-like planet would induce in its host star, expecting to find worlds orbiting far out on multi-year orbits, just like the giant planets in our own backyard. That is not what happened. In 1992, radio astronomer Alexander Wolszczan and his collaborator Dale Frail announced something nobody had anticipated: planets orbiting a pulsar, the collapsed, rapidly spinning corpse of a star that had already exploded as a supernova. This was about as far from the solar system template as you could get. A pulsar is not even really a star anymore. It is an ultra-dense neutron star, roughly the size of a city, spinning many times per second and blasting out beams of radiation like a cosmic lighthouse. Finding planets there was bizarre, almost beyond words, and yet it happened first. A few years later, in 1995, Swiss astronomers Michel Mayer and Didier Queloz found the first planet orbiting a normal Sun-like star, but once again, nature refused to follow the script. The planet, given the name 51 Pegasi b, was a gas giant roughly half the mass of Jupiter, and it completed a full orbit around its star in just 4.2 days. For comparison, Mercury, the innermost planet in our solar system, takes 88 days to orbit the Sun, this new planet was orbiting more than 10 times closer to its star than Mercury does to ours, baking at temperatures exceeding 1,000 degrees Celsius. Astronomers had a name ready for this new and startling class of world, the hot Jupiter, a gas giant that, according to standard planet formation theory, should never have been able to form so close to its star, since the intense heat that near a star should prevent the accumulation of the ices and gases needed to build a giant planet in the first place. The leading explanation today is that these worlds formed farther out, in the colder regions predicted by the old theories, and then migrated inward over time, spiraling closer to their stars through gravitational interactions with the surrounding disk of gas and dust, or through interactions with other planets that flung them onto tighter, more eccentric orbits that gradually circularized close to the star. Here is the striking part. We now know, thanks to 2 decades of additional exoplanet surveys, including the incredibly productive Kepler Space Telescope, that hot Jupiters are actually quite rare. Careful statistical surveys suggest that less than 1% of Sun-like stars host a hot Jupiter. And yet, throughout the 1990s and into the early 2000s, these bizarre, scorching worlds dominated the growing catalogue of known exoplanets. For years, if you asked someone to picture an alien solar system, you would probably picture something built around a hot Jupiter, precisely because that is virtually all astronomers had actually found. Why did such a rare category of world so thoroughly dominate the early exoplanet catalogue? The answer is, once again, detection bias, though this time it operates through a slightly different mechanism than the Malmquist effect governing what stars we can see with the naked eye. The main technique used to find those early exoplanets was the radial velocity method, which detects the tiny gravitational tug a planet exerts on its host star, causing the star to wobble back and forth in a way that shifts its light very slightly toward the red and then the blue as it moves away from and toward us. The size of that wobble depends on the planet's mass and how close it orbits. A massive planet on a tight, fast orbit produces a large, easily measured, frequently repeating signal as small planet on a slow, wide orbit, like an actual Jupiter analog around a Sun analog, produces the faintest of wobbles, one that might take 12 years just to complete a single detectable cycle, well beyond the patience or funding cycle of most early observational campaigns. In other words, the very worlds we expected to find, ordinary gas giants in ordinary distant orbits, were precisely the hardest to detect, while their strange, rare, superheated cousins orbiting close and fast screamed out their presence in a matter of days. The same story repeats with the transit method, the technique that eventually powered the Kepler mission's extraordinary haul of thousands of confirmed exoplanets. A transit is detected when a planet passes directly in front of its star from our vantage point, causing a small periodic dip in the star's observed brightness. Planets on short orbits transit frequently, giving astronomers many repeated dips to confirm a detection quickly. Planets on long, wide orbits transit rarely, sometimes only once every several years, and a single dip is not enough to confirm anything. Once again, close-in worlds triumph in the discovery statistics, not because they are common, but because their orbital geometry makes them dramatically easier to catch in the act. The picture that emerges from all of this is remarkably consistent. Pulsar planets, hot Jupiters, giant stars, and, as we are about to see, supernovae are not typical examples of their respective categories. They are extreme outliers, the exceptions rather than the rule, but their extremity is precisely what makes them detectable. They are, in a sense, the loud guests at a party who dominate every conversation purely through volume. Even though most of the room is filled with quieter people going about their business unnoticed. Supernovae make this point even more forcefully than planets or stars do. The most common variety, a core collapse supernova, marks the violent death of a star at least 8 times the mass of the Sun for most of a massive star's life. It exists in a delicate balance. The inward crush of its own gravity is held at bay by the outward push of radiation pressure generated by nuclear fusion in its core. Hydrogen fuses into helium, helium into carbon and oxygen, and in the most massive stars this chain continues all the way up through silicon fusing into iron. Iron is the dead end. Fusing iron does not release energy. It consumes it. Once a massive star builds up an iron core, fusion can no longer hold back gravity, and the core collapses in on itself in well under a second, crushing down into a neutron star, or in the most massive cases, a black hole. The outer layers of the star, still falling inward, slam into the newly formed dense core and rebound outward in a shockwave, blasting the star's remaining material into space in one of the most energetic events in the universe. For a period of days to weeks, a single exploding star can outshine every other star in its host galaxy combined, radiating as much energy in that time as the Sun will produce over its entire 10 billion year lifetime. And yet, despite this staggering output, core collapse supernovae are individually rare events. In a galaxy the size of the Milky Way, containing on the order of 100 billion stars, a supernova of any kind occurs on average only about once every 50 years. Given that rarity, you might expect astronomers to have witnessed only a handful of these events throughout the history of the field. Instead, modern astronomical surveys catalogue many thousands of supernovae every single year. The explanation is once again pure detectability. A supernova's extraordinary brightness allows it to be seen not just across our own galaxy, but across enormous cosmological distances in galaxies billions of light years away, far beyond the reach of ordinary starlight. By scanning enormous swaths of the sky and enormous numbers of distant galaxies simultaneously, wide-field surveys effectively multiply their odds of catching one of these rare explosions. Because although any single galaxy only produces one every few decades, there are countless galaxies to watch. There is a useful piece of physics underlying why brightness translates so powerfully into detectability, and it is worth walking through because it explains just how dramatically a modest increase in luminosity can translate into an enormous increase in discoverability. Consider a telescope of fixed sensitivity, capable of detecting any object above some minimum brightness as measured from Earth. Because light spreads out and dims according to the inverse square of distance, an object twice as intrinsically luminous as another can be detected from roughly 1.4 times farther away. The square root of 2, but detectability is not just about the maximum distance at which something can be spotted. It is about the volume of space being searched, and volume scales with the cube of distance. So if a brighter object can be seen twice as far away, the volume of space within which it could be sitting and still be detected grows by a factor of 2 cubed, or 8 in general, for objects of fixed intrinsic brightness spread evenly through space. The number you can detect scales with luminosity raised to the power of 3/2. Because luminosity determines the maximum detectable distance through an inverse square law, and the detectable volume in turn scales as the cube of that distance, and taking the square root inherent in the distance relation combined with the cube of volume works out to a 3/2 power law overall. The practical upshot is almost absurd. An object just 100 times more luminous than another does not become 100 times more detectable. It becomes roughly 1,000 times more detectable. Because you are now searching a vastly larger volume of space for it, this is precisely why brief, blindingly bright events like supernovae get discovered so disproportionately often compared to the vastly more numerous, but far dimmer, stable stars quietly burning away in the depths of interstellar space. So here is the pattern. Laid out plainly, pulsar planets are strange and rare, but their existence around a source as unmistakable as a pulsar made them impossible to miss. Hot Jupiters are strange and rare, but their tight, fast orbits produce signals that dwarf those of ordinary gas giants on ordinary orbits. Giant stars are strange and rare, making up roughly 1% of the galactic stellar population, yet their tremendous luminosity lets them dominate what is visible to the naked eye from Earth. And supernovae are the most extreme example of all, transient explosions so overwhelmingly bright for such a short window of time that they get discovered by the thousands across the observable universe, despite each individual galaxy producing one only once every few decades. The common thread running through every one of these cases is this: it is not typical members of a population that get discovered first. It is the extreme outliers, whatever quality makes them extreme, whether that is proximity to a bizarre host object, orbital tightness, sheer luminosity, or explosive energy output. Ordinary, well-behaved members of a population, however numerous they might actually be, tend to hide in plain sight simply because they do not produce a strong enough signal to stand out against the noise and distance of the universe. Which brings us to the real question this pattern raises. If this bias has held true for planets, stars, and stellar explosions, should we expect it to hold true for the search for extraterrestrial intelligence as well? If alien civilizations exist scattered throughout the galaxy, is it plausible that the first one humanity detects will not be a typical, quiet, long-lived, sustainably operating society, but instead some kind of extreme outlier, a civilization behaving in a way that is dramatically atypical? But precisely because of that atypical behavior, extraordinarily loud? To answer that question, it helps to ask what the civilizational equivalent of a supernova would actually look like. A supernova, at its core, is a star violently departing from equilibrium. For billions of years, the star sat in a stable balance between gravity and radiation pressure, unremarkable, blending into the background hum of 100 billion other stars just like it. What made it detectable across cosmological distances was precisely the moment that balance broke down catastrophically. Extend that logic to a technological civilization, and a natural hypothesis falls out. A civilization that has fallen out of equilibrium with its environment, whether energetically, environmentally, or technologically, might likewise become disproportionately detectable, for exactly the same underlying reason that a dying star does. Disequilibrium in this sense could mean many things. It could mean a civilization whose energy consumption is expanding so quickly that it radiates a very unusual and very rapidly changing pattern of waste heat into space. It could mean a civilization whose industrial activity is altering its planet's atmospheric chemistry at a rate that has no natural geological analog, something scientists studying our own planet are watching happen in real time. It could mean a civilization actively re-engineering the surface of its world, or constructing megastructures to capture more of its star's energy output. Or in the most extreme and dramatic case imaginable, it could mean a civilization at war with itself, deploying weapons capable of releasing planetary-scale amounts of energy in a matter of minutes. Each of these scenarios shares the same underlying structure as our astronomical examples. They are unusual departures from a long-term steady state, and it is precisely their unusualness, their sheer energetic loudness, that would make them detectable across interstellar distances in ways that a quiet, sustainable, energy-efficient civilization simply would not be. Consider humanity's own current situation as a case study, because it maps onto this framework almost too neatly. Over the past 2 centuries, but especially over the past several decades, human industrial activity has driven measurable, rapid changes in Earth's atmospheric composition, average global temperature, and land use patterns. Atmospheric carbon dioxide concentrations have risen from around 280 parts per million in the pre-industrial era to over 420 parts per million today, a change occurring on a timescale of mere centuries, a blink of an eye in geological terms. In principle, A sufficiently advanced observer studying Earth's atmosphere from a distant star system, using something like transit spectroscopy to analyze the light filtering through our atmosphere as our planet passes in front of the Sun from their point of view, could in theory detect this kind of chemical disequilibrium as an anomalous signature, a marker that something unusual and non-geological is actively altering the planet's atmospheric chemistry. This is, in fact, one of the seriously proposed methods by which astrobiologists suggest we might detect industrial activity on other worlds. Not a deliberate radio broadcast, but an inadvertent chemical fingerprint, industrial gases or their byproducts that have no plausible natural source and that appear in unusual, non-equilibrium concentrations. The James Webb Space Telescope and its successors are, in a limited sense, already searching for such biosignatures and potential technosignatures in the atmospheres of nearby exoplanets. Though the technology for confidently identifying industrial pollutants specifically, as opposed to broader biosignature gases like oxygen or methane, remains in its early stages. A far more extreme and far more sobering example of civilizational disequilibrium would be global nuclear war. If every nuclear weapon currently held in humanity's various arsenals were detonated simultaneously, the resulting flash of energy, along with the subsequent radioactive and atmospheric disturbances, would in principle be detectable by a sufficiently sensitive and sufficiently attentive observer elsewhere in the galaxy. At least for a brief window of time, this is not merely a thought experiment invented for dramatic effect. In 1971, the American astronomer James Elliott, working alongside colleagues studying the search for extraterrestrial intelligence, floated a genuinely serious proposal along these lines: detonate the world's nuclear arsenal deliberately, in a controlled and directed manner, as an unmistakable signal broadcast to the rest of the galaxy, simultaneously ridding the planet of its most destructive weapons and announcing humanity's existence to the cosmos in the loudest way physically available to us at the time. The proposal never gained serious traction for reasons that should be fairly obvious, but it illustrates the underlying logic with startling clarity. Detonating a planet's entire nuclear stockpile represents about as extreme a departure from equilibrium as a civilization could manage, and following the three-halves power law we walked through earlier, that brief burst of extreme loudness would make such an event vastly, disproportionately more detectable than the same civilization's ordinary, quiet, day-to-day existence, even though the destructive act itself might only last for a matter of minutes. Between these two extremes, gradual atmospheric change on one end and planetary self-annihilation on the other, lies a whole spectrum of possible disequilibrium signatures a civilization might produce as it grows, industrializes and expands its energy consumption. Physicist Freeman Dyson proposed one of the more famous hypothetical examples back in 1960. He suggested that a sufficiently advanced civilization, seeking to capture as much of its star's energy output as possible, might eventually construct a vast structure or swarm of structures encircling its entire star to harvest the majority of its radiated power. Such a structure, now commonly referred to as a Dyson sphere or Dyson swarm, would necessarily radiate an enormous amount of waste heat as a byproduct of thermodynamics, since no energy capturing process can be perfectly efficient. That waste heat would show up not as visible light, but as an excess of infrared radiation, a telltale thermal glow that would not match the expected profile of an ordinary star, and that in principle could be picked out by infrared survey telescopes scanning large numbers of stars for anomalies. Several targeted searches for such infrared excesses have already been conducted using data from infrared survey missions, and while none have turned up a confirmed Dyson structure, the search itself represents a genuine, serious application of exactly the kind of detectability through disequilibrium logic being described here. A star surrounded by a massive energy harvesting structure would be, in a very real sense, a civilization in a state of engineered energetic disequilibrium with its natural surroundings. And that disequilibrium is precisely what would make it stand out against the billions of ordinary, structurally unmodified stars around it. This idea connects naturally to a concept that has circulated in the search for extraterrestrial intelligence community for some time, sometimes referred to as the sustainability solution to the Fermi Paradox. The puzzling observation first articulated by physicist Enrico Fermi in 1950 that given the vast number of stars and the vast age of the galaxy, intelligent civilization should statistically be common and should have had plenty of time to expand and become detectable. And yet, so far, we have found no confirmed evidence of any of them at all. The sustainability solution offers one possible explanation, and it works something like this. Imagine a thermal image, the kind captured by an infrared camera of a poorly insulated apartment building on a cold winter night. Bright patches of red and orange bloom across the image everywhere. Heat is leaking wastefully out through windows, walls, and roofing. That leaking heat is energy the building's occupants paid for and are now losing to the surrounding environment. Unused and unwanted purely as a byproduct of inefficient engineering, engineers who design more efficient buildings work specifically to minimize exactly this kind of thermal leakage. A perfectly insulated, perfectly efficient building would, in the limit, radiate essentially no excess waste heat at all. It would become thermally invisible, blending seamlessly into the ambient temperature of its surroundings. Now scale that same logic up to an entire civilization. A young, rapidly industrializing society, still working out efficient ways to generate, store, and use energy, will inevitably leak a great deal of that energy as waste, in the form of heat, light pollution, atmospheric byproducts, and electromagnetic emissions of every kind, including the sort of unintentional radio and television broadcasts that Earth itself began leaking into space starting in the 1930s and 1940s. But a civilization that survives long enough and matures technologically far enough would have every incentive to become dramatically more efficient over time, both because efficiency conserves scarce resources and because efficiency is, in a purely engineering sense, simply better design. Taken to its logical extreme, a sufficiently advanced, sufficiently mature civilization might become so energy efficient, so environmentally integrated, and so quiet across the electromagnetic spectrum that it would produce essentially no detectable signature at all, indistinguishable from an ordinary, uninhabited world. The Canadian science fiction author Carl Schroeder captured this idea in a phrase that has since become something of a touchstone within the field, offering a deliberate twist on Arthur C. Clarke's much older and more famous observation that any sufficiently advanced technology is indistinguishable from magic. Schroeder's version states instead that any sufficiently advanced civilization is indistinguishable from nature. The implication is unsettling in its own quiet way. There could be highly advanced, long-lived, thriving alien civilizations scattered throughout the galaxy right now, and we would have no way of detecting a single one of them, not because they are hiding deliberately, but simply because true technological maturity looks from the outside exactly like the absence of technology altogether. Putting these two threads together, the detection bias pattern drawn from the history of astronomy and the sustainability solution drawn from the search for extraterrestrial intelligence produces a genuinely striking hypothesis about first contact. If mature, sustainable civilizations really do become progressively quieter and harder to detect the longer they endure, while young, unstable, or self-destructing civilizations become dramatically louder during whatever brief period of disequilibrium they pass through. Then the very same detection bias that has shaped every major discovery in the history of observational astronomy should apply here as well. The civilizations most likely to be discovered first would not be the calm, quiet, long-term survivors. They would be the loud, unstable, temporary outliers, civilizations caught in the act of some kind of dramatic, energetic, or environmental upheaval. Whether that upheaval stems from runaway industrial growth, environmental collapse, large-scale warfare, or the energetically intensive process of constructing a massive engineering project like a Dyson swarm. This idea deserves a name, and the most fitting one draws from the ancient Greek word eschatos, meaning last, or the end of all things, the same root that gives us the term eschatology, the study of ultimate destinies and final events. We can call this the Escation Hypothesis. It is a deliberately loaded name, because baked directly into the premise is the recognition that any period of extreme energetic disequilibrium is, almost by definition, unsustainable. A civilization cannot burn through resources at a wildly unsustainable rate forever, any more than a supernova can keep exploding indefinitely. One way or another, this loud, detectable phase has to end. It might end because the civilization successfully transitions to a more sustainable and therefore quieter mode of existence. It might end because the underlying instability that produced the disequilibrium in the first place, whether environmental collapse, resource exhaustion, or internal conflict, ultimately causes the civilization itself to collapse or destroy itself. Either way, the loud, detectable signal represents a genuinely transitory phase, a narrow window in a civilization's long-term history, during which it happens to be shouting into the void, whether it intends to or not. It is worth being precise about what this hypothesis is claiming, and equally important, what it is not claiming. It is not asserting that quiet, sustainable civilizations do not exist, or that they are somehow rarer than loud, unstable ones. In fact, the opposite is almost certainly true, in exactly the same way that ordinary, sun-like stars vastly outnumber giant stars, and ordinary, cooler exoplanets on wide orbits almost certainly outnumber hot Jupiters. The hypothesis instead makes a claim purely about detectability, about which type of civilization is statistically most likely to be the first one humanity actually stumbles across, given the tools and methods available to us, regardless of which type is actually more numerous across the galaxy as a whole. Whether that claim holds up depends on a genuine, unresolved trade-off between three separate factors, and it is worth being honest that we do not currently know the answer to any of them with confidence. The first factor is the fraction of civilizations that pass through some kind of loud, unstable disequilibrium phase at all, as opposed to civilizations that manage to industrialize gradually and sustainably from the outset, never producing a strong, anomalous signal in the first place. The second factor is exactly how detectable such a phase actually becomes while it lasts. Since not every form of disequilibrium is equally loud, industrial waste heat is far subtler than a burst of gamma radiation from a directed weapon, for instance. And the third factor is simply how long such a phase persists before it either resolves into stability or ends in collapse. Since a signal lasting only a few minutes, like a nuclear detonation, is far less likely to be caught by any given observer than a signal lasting a few centuries, like a slow-building greenhouse effect. The product of those three factors, roughly speaking, how many civilizations go loud, how loud they get, and for how long, determines the overall detection probability contributed by unstable civilizations. That combined probability then has to be weighed against the competing detection probability contributed by the presumably far more numerous, but far quieter, population of stable, sustainable civilizations that may be sitting silently throughout the galaxy, producing next to no signal at all. The Escation Hypothesis proposes that, much like hot Jupiters and pulsar planets before them, the loud, unstable minority will end up dominating our actual detections, purely because of how disproportionately visible they become during their brief window of instability, even if they represent only a small slice of the total civilizational population out there. But this remains a genuinely open question, not a settled conclusion, and it is entirely possible that quiet civilizations, despite their lower individual detectability, are numerous enough to win out in aggregate anyway, the same way that ordinary faint stars, despite being individually far harder to spot than giants, still outnumber the visible giants in any complete, Unbiased galactic census taken with sufficiently powerful instruments rather than the naked eye. It is useful to place the Escation Hypothesis alongside the other major proposed solutions to the Fermi Paradox, because doing so helps clarify exactly what kind of explanation it actually is. One long-standing proposal, known as the Rare Earth Hypothesis, suggests that the specific combination of conditions required for complex, intelligent life to arise, a stable host star, a planet in the right orbital zone, a large moon to stabilize axial tilt, plate tectonics, a protective magnetic field, and a long, uninterrupted evolutionary history free of extinction-level catastrophes, might simply be far rarer across the galaxy than early. Optimistic estimates assumed, under this view, we have not detected other civilizations because there may be very few of them to detect in the first place. A second major proposal, known as the Great Filter, suggests that somewhere along the long evolutionary path from simple self-replicating chemistry to a spacefaring, galaxy-colonizing civilization, there exists at least one exceptionally difficult transition, a filter that most potential civilizations fail to pass through. The unsettling open question embedded in the Great Filter concept is whether that filter lies somewhere behind humanity, in our evolutionary past, meaning we have already beaten the odds and cleared the hardest step, or whether it lies somewhere ahead of us, meaning our own eventual extinction or technological self-destruction might still be waiting for us, just as it may have already claimed every other civilization that ever tried to industrialize. A third proposal, sometimes called the Zoo hypothesis, suggests that advanced civilizations may already be aware of humanity's existence but are deliberately avoiding contact, whether out of some kind of non-interference principle or out of simple disinterest, or as a precaution against unknown risks associated with revealing themselves. The Escation hypothesis does not directly compete with any of these. It operates somewhat orthogonally to all three, addressing a different question entirely. Rather than asking why civilizations might be rare, or why some evolutionary transition might be difficult to pass, or why an existing civilization might choose to hide, it asks a narrower, more specific, more empirically grounded question, assuming a mixed population of civilizations at various stages of development and various states of internal stability genuinely exists out there somewhere. Which type is statistically most likely to be the first one humanity's instruments actually happen to catch? And on that narrower question, the long track record of detection bias throughout the history of observational astronomy offers a genuinely useful, if unsettling, guide. Everything discussed so far treats a civilization's detectable signal as something essentially accidental, a byproduct of energy use, industrial activity, or catastrophic self-destruction radiated outward without any intention of being noticed. In the same way a supernova has no intention of being seen, but there is a second, more deliberate version of the Escation hypothesis worth considering, one in which a civilization facing its own internal collapse consciously chooses to transmit a signal outward, specifically because it recognizes that its own end may be approaching. The logic here connects to a genuine and long-running debate within the search for extraterrestrial intelligence community over whether humanity should be actively transmitting deliberate signals into space at all, a practice generally referred to as messaging extraterrestrial intelligence, distinct from simply listening for signals sent by others. The physicist Stephen Hawking was among the most prominent voices warning against this practice, arguing on several occasions throughout his life that broadcasting our location and technological capability to unknown civilizations could be a profound risk. Drawing a loose historical parallel to encounters between technologically mismatched human societies throughout our own history, encounters which did not, on the whole, go well for the less advanced party. This concern found a particularly vivid fictional treatment in Chinese author Liu Cixin's novel The Three-Body Problem, and its sequels, which popularized what has come to be known as the dark forest theory of interstellar civilization. Under this framework, the galaxy is imagined as a dark forest in which every civilization is simultaneously a potential predator and a potential prey, and in which the safest possible strategy for any civilization is to remain as silent and undetectable as possible, since revealing your location to an unknown and potentially far more powerful civilization carries an unacceptable risk of annihilation, with no way to verify the intentions or capabilities of whoever might be listening before it is far too late to take the warning back. But the Escation Hypothesis offers an interesting wrinkle to this otherwise fairly pessimistic calculation. The dark forest argument for staying silent rests fundamentally on a cost-benefit analysis. The potential benefit of contact, cultural exchange, scientific knowledge, cooperation, has to be weighed against the potential existential risk of exposing yourself to a hostile, more powerful civilization. That calculation changes dramatically, however, for a civilization that is already facing its own internal collapse or extinction through some other cause entirely, whether environmental catastrophe, resource exhaustion, or self-inflicted conflict. For such a civilization, the usual argument for staying silent, the fear of provoking external annihilation, carries far less weight because annihilation, in some form, may already be underway internally or may already be effectively unavoidable. Under those specific and admittedly grim circumstances, a civilization facing its own end might have very little left to lose, and potentially quite a lot to gain, by broadcasting a final, deliberate signal outward, an attempt at contact, an attempt to be remembered, an attempt to pass on accumulated knowledge, or simply a final desperate cry for help, launched in the hope that some more capable civilization might somehow intervene in it. Time. This admittedly speculative scenario adds an intriguing dimension to one of the most famous, unresolved mysteries in the history of the search for extraterrestrial intelligence, the WOW signal. On August 15, 1977, astronomer Jerry Amon, working with Ohio State University's Big Ear radio telescope as part of an ongoing search for extraterrestrial radio signals, recorded an extraordinarily strong narrowband radio signal lasting approximately 72 seconds. Arriving from the direction of the constellation Sagittarius, the signal was roughly 30 times stronger than the background noise level, an intensity so striking that Amon circled the corresponding printout data and wrote the single word "wow" in the margin, giving the event its enduring name. Despite extensive follow-up observations conducted over the following decades, the signal has never been detected again, and to this day, no fully satisfying natural or artificial explanation has been confirmed. Various proposed explanations have included a passing comet outgassing hydrogen, an artifact of the receiving equipment itself, or, at the far more speculative end of the spectrum, an actual deliberate or incidental transmission from an extraterrestrial source. Under the specific framework we have been building throughout this discussion, one could imagine, purely as speculation and nothing more, that a brief, powerful, one-time signal, like the WOW signal, might be consistent with exactly the kind of short-lived, high-intensity, non-repeating transmission that a civilization in the midst of some kind of terminal crisis, deliberately or otherwise, might produce. This is not offered as a claim that the WOW signal actually was such a transmission, since the honest and far more likely explanation remains a natural astrophysical phenomenon or an instrumental artifact that has simply never been fully identified. But the episode nonetheless serves as a useful illustration of the broader principle at work throughout the Escation Hypothesis. The signals we are most likely to actually catch, whether accidental or deliberate, whether from a civilization in industrial upheaval or in outright collapse, are likely to be brief, powerful, and frustratingly non-repeating, precisely because sustained, stable, long-term signals require a sustained, stable civilization to keep producing them, and sustained stability. According to the sustainability solution discussed earlier, is exactly the condition under which a civilization becomes progressively quieter and harder to detect over time. not louder. If there is genuine merit to this hypothesis, it carries real, practical implications for how the search for extraterrestrial intelligence ought to be conducted going forward, implications that align surprisingly well with where observational astronomy has already been heading over the past decade, largely for entirely unrelated scientific reasons. If loud, unstable civilizations really are the most detectable category, and if their loudness manifests as a short-lived transient event, whether a burst of unusual electromagnetic radiation, a rapid and anomalous change in a planet's atmospheric chemistry, or an unexplained brightening or dimming pattern in a star's light curve, then the optimal search strategy is not to stare fixedly at a small handful of individually promising star systems for years on end, hoping to catch a sustained, repeating signal. The optimal strategy is instead to scan as much of the sky as possible, as frequently as possible, across as many different wavelengths as possible, purely in order to maximize the odds of happening to be looking in the right place at the right moment when a brief, anomalous event occurs somewhere out there. This is essentially exactly the observing philosophy behind several of the most ambitious astronomical survey projects currently underway or recently completed. The Vera C. Rubin Observatory, situated in the mountains of Chile and beginning full science operations in the current decade, is specifically designed to conduct what astronomers call a time domain survey, repeatedly imaging the entire visible southern sky roughly every 3 to 4 nights using an extraordinarily wide field of view and an exceptionally large digital camera, in order to catch precisely the kind of transient, short-lived astronomical events that a slower, more narrowly targeted survey would inevitably miss. Although Rubin's primary scientific goals center on mapping dark matter and dark energy, cataloging asteroids within our own solar system, and studying the structure of the Milky Way, its fundamentally transient-focused observing strategy makes it, almost as an incidental side benefit, one of the best-positioned instruments in existence for catching an unexpected, brief techno-signature. Exactly the kind of anomalous event the Escation Hypothesis predicts would be most likely to represent our actual first evidence of another civilization. Radio astronomy has followed a broadly similar trajectory. The Breakthrough Listen initiative, launched in 2015 with substantial private funding, conducts systematic radio and optical searches across large numbers of star systems, and has progressively expanded its search strategy to cover wider swathes of sky and broader ranges of frequency. Rather than narrowly focusing observing time on a small handful of individually promising, sun-like stars, precisely because a broad, generalized search is far better suited to catching an unpredictable, transient signal than a narrow, targeted one would be. There is a deeper irony worth sitting with here, one that connects this entire discussion back to its very starting point. Just as astronomers can look up at giant stars scattered across the night sky and recognize them as a preview of what our own sun will eventually become, roughly 5 billion years from now, when it exhausts its core hydrogen fuel and swells into a red giant large enough to engulf Mercury, Venus, and quite possibly Earth itself, so too might any loud, unstable, disequilibrium signal civilizations we eventually detect elsewhere in the galaxy represent a kind of preview, a mirror held up to humanity's own possible future. Right now, in the present moment, human civilization is arguably passing through exactly the kind of energetic and environmental disequilibrium the Escation Hypothesis describes: rapidly rising energy consumption, rapid and historically unprecedented changes to atmospheric chemistry and global climate, and the continued existence of nuclear arsenals capable of producing exactly the kind of catastrophic, high-energy transient event discussed earlier. Whether humanity's current trajectory ultimately resolves into a long-term, sustainable and by extension quieter and less detectable civilization, or instead culminates in some form of environmental or technological collapse, is a question we are, in a very real and immediate sense, still actively answering through our own choices right now, in real time. This gives the search for extraterrestrial intelligence an unexpectedly reflective quality that goes well beyond simple scientific curiosity. If astronomers do eventually detect a genuine techno-signature from a distant civilization, and if that signature does turn out to bear the hallmarks of the Escation Hypothesis, a brief, energetic, non-repeating signal consistent with a civilization in the midst of some kind of terminal upheaval, that detection would carry a sobering implication far beyond simply confirming that we are not alone in the universe. It would also, quite possibly, be showing humanity a preview of one of its own potential futures, in the same way that observing a red giant star today lets us glimpse the sun's own inevitable fate written across the night sky, 5 billion years ahead of schedule. To understand why energy consumption specifically makes such a natural marker of civilizational disequilibrium, it helps to look at a classification system astronomers and physicists have used for decades to think about the growth trajectory of technological civilizations. In 1964, Soviet astronomer Nikolai Kardashev proposed a framework, now known as the Kardashev scale, for categorizing hypothetical civilizations according to the total amount of energy they are able to harness and put to use. A Type 1 civilization under this scheme is one capable of harnessing and utilizing roughly all of the energy available on its home planet, an amount on the order of 100 quadrillion watts, drawing on solar energy reaching the planet's surface, along with geothermal, wind, and other planetary energy sources. A Type 2 civilization is one capable of harnessing the entire energy output of its home star, on the order of 400 septillion watts in the case of a Sun-like star, an amount roughly 10 billion times greater than what a Type 1 civilization commands, and a Type 3 civilization is one capable of harnessing the energy output of its entire home galaxy, a staggering figure on the order of tens of trillions of times greater still. By this classification, human civilization currently sits at somewhere around Type 0.7, meaning we have not yet fully mastered even the energy resources available on our own planet, let alone begun meaningfully tapping into the sun's much larger output. But what makes the Kardashev framework genuinely relevant to the Escation Hypothesis is not simply the raw energy numbers themselves, but the transition process implied by climbing from one level to the next, moving from a Type 0.7 civilization toward a true Type 1 civilization necessarily requires a dramatic, rapid increase in total energy throughput, and history strongly suggests that rapid increases in energy throughput tend to be messy, inefficient, and environmentally disruptive, at least during the earlier phases of that transition. Before more efficient technologies and more sustainable practices have had time to mature and become widely adopted, human civilization's own trajectory over roughly the past 2 centuries illustrates this pattern clearly. The large-scale burning of fossil fuels, beginning with coal in the 18th and 19th centuries and expanding dramatically with oil and natural gas throughout the 20th century, enabled an explosive, historically unprecedented expansion in total available energy, powering industrialization, electrification, mechanized agriculture, and eventually a global technological civilization capable of instantaneous worldwide communication and space travel. But that same explosive energy expansion has come bundled with a set of serious, and still largely unresolved, environmental disequilibria, rapidly rising atmospheric carbon dioxide concentrations, measurable global average temperature increases, ocean acidification, and widespread disruption of natural ecosystems, all occurring far more rapidly than the planet's natural systems have historically had to accommodate. If an alien civilization elsewhere in the galaxy followed a broadly similar developmental arc, and there is no particular reason grounded in physics or chemistry to assume it would not, given that the underlying thermodynamic and engineering trade-offs involved in extracting and using large amounts of energy efficiently are presumably fairly universal, then we might reasonably expect many, if not most, technological civilizations to pass through some version of this same disequilibrium phase during their own climb up the Kardashev scale. The interesting and genuinely open question the Escation Hypothesis raises is what fraction of civilizations successfully navigate through that disequilibrium phase and emerge on the other side as a stable, sustainable and by extension quieter Type 1 or Type 2 civilization, versus what fraction instead succumb to the disequilibrium itself, through environmental collapse, resource exhaustion, large-scale conflict over dwindling resources, or some other self-inflicted catastrophe before ever reaching that more stable, sustainable state on the other side. This framing also helps clarify an important subtlety embedded in the earlier discussion of Dyson spheres and megastructures. Constructing a Dyson swarm capable of capturing a meaningful fraction of a star's total energy output would represent an absolutely enormous engineering undertaking, requiring the disassembly or extensive mining of significant amounts of planetary or asteroid material, and almost certainly requiring centuries, if not millennia, of sustained industrial effort to complete. During that extended construction phase, a civilization would very plausibly radiate substantial excess waste heat and other detectable byproducts as an unavoidable consequence of the sheer scale of industrial activity involved, even if the civilization's ultimate long-term goal, once construction is finally complete, is precisely the kind of efficient, low-waste energy harvesting that a mature Type 2 civilization would presumably want to achieve. In other words, the very act of transitioning toward a more advanced, more energy-efficient state might itself constitute exactly the kind of loud, detectable, disequilibrium phase the Escation Hypothesis identifies as our best chance of detection, even for a civilization that is not remotely on the verge of collapse, but is instead simply in the middle of a long, resource-intensive but ultimately successful engineering project. The pattern of extreme outliers dominating astronomical discovery did not stop with planets, giant stars, and supernovae. It continued to reassert itself with almost every major new class of astronomical phenomenon discovered over the past half-century, and walking through a few more of these cases helps reinforce just how consistent and reliable this bias has proven to be. Take gamma-ray bursts, first detected accidentally in the late 1960s by American military satellites called Vela, which had actually been launched to monitor for secret nuclear weapons tests being conducted in violation of international treaties. Instead of catching evidence of clandestine nuclear detonations on Earth, the satellites picked up brief, intense flashes of gamma radiation arriving from deep space far beyond the solar system. It would take decades of subsequent observation to determine what these bursts actually were. Two distinct classes of extraordinarily energetic explosions, one associated with the collapse of the most massive stars into black holes, and another associated with the violent merger of two neutron stars. A single gamma-ray burst can release more energy in a matter of seconds than the sun will radiate over its entire multi-billion-year lifetime, making it, for that brief window of time, one of the most luminous single events in the observable universe. And yet, exactly as with supernovae, the specific stellar collapse and merger events that produce gamma-ray bursts are individually quite rare. Their overwhelming energy output is precisely what allows them to be detected from galaxies billions of light-years away, far beyond the range at which any ordinary stellar process could ever be observed. Meaning that gamma-ray bursts, despite representing an exceptionally rare category of astrophysical event, have become one of the most frequently catalogued types of transient phenomena in modern observational astronomy, purely as a consequence of their extreme brightness. A more recent example, and one still actively being studied today, is the fast radio burst, a class of astrophysical phenomenon first identified in 2007 and confirmed as a genuinely new category of event in the years that followed. Fast radio bursts are extraordinarily brief, typically lasting only a few milliseconds. Flashes of intense radio emission arriving from sources located in distant galaxies, often billions of light-years away, despite their brevity, individual fast radio bursts release as much energy in those few milliseconds as the sun produces over an entire day or longer. Their precise origin remains an active area of ongoing research, with the leading hypothesis centering on magnetars, an extraordinarily rare type of neutron star possessing the strongest magnetic fields known anywhere in the universe, though some fast radio bursts appear to repeat from the same source, while others appear to be genuine one-off events, suggesting more than one underlying physical mechanism may be responsible for producing them, regardless of the precise mechanism. The same underlying pattern holds, an intrinsically rare, exotic astrophysical process, made detectable across cosmological distances purely because of its extreme, if brief, energy output has, within less than 2 decades of its initial discovery, become one of the more actively studied areas of modern radio astronomy, with dedicated survey telescopes now cataloguing thousands of individual bursts. Even at the scale of entire galaxies, this same bias reasserts itself. Quasars, among the most luminous individual objects known anywhere in the universe, are powered by supermassive black holes actively accreting, meaning rapidly consuming, large quantities of surrounding gas and dust at the centers of certain galaxies. As that infalling material spirals inward toward the black hole, it heats to extraordinary temperatures through friction and gravitational compression, radiating enormous quantities of energy across the entire electromagnetic spectrum, often outshining every star in the host galaxy combined by a wide margin. But this actively accreting, quasar-producing phase represents only a relatively brief period in the overall lifespan of a supermassive black hole, since the surrounding reservoir of easily accessible infalling gas eventually depletes, or gets consumed, or gets gravitationally disrupted and scattered by other processes within the galaxy, after which the black hole settles into a much quieter, largely dormant state, exactly like the one that the supermassive black hole at the center of our own Milky Way galaxy currently occupies. And yet, because quasars are so extraordinarily luminous, they have been detected across the vast majority of the observable universe, providing astronomers with some of their most valuable evidence about conditions in the very early universe. Conditions that would otherwise be almost entirely inaccessible to direct observation given the sheer distances and correspondingly enormous light travel times involved. Quiet, dormant, supermassive black holes, the overwhelmingly more common state for such objects, are, by comparison, exceptionally difficult to detect directly at all, precisely because a black hole that is not actively consuming surrounding material radiates almost no light of its own, blending invisibly into the darkness of its host galaxy's center. 4 separate categories of astrophysical phenomena, then planets, stellar explosions, millisecond radio flashes, and actively accreting supermassive black holes all tell fundamentally the same story, at wildly different physical scales and through entirely different underlying mechanisms. The rare, extreme, energetically disequilibrium-driven outliers within each category consistently and dramatically dominate what actually gets discovered, catalogued and studied, while the far more numerous, but far quieter and more stable, typical members of each category remain comparatively hidden, underrepresented and in some cases still almost entirely unstudied directly, simply because they do not produce a strong enough signal to punch through the technical limitations and finite observing time available to any real astronomical survey. It is worth stepping back briefly to look at where the underlying question this whole discussion is built around actually came from, because the history helps explain why so many competing hypotheses, including this one, have accumulated around it over the decades. The story is often told as a lunchtime conversation. In the summer of 1950, physicist Enrico Fermi was having lunch with several colleagues at Los Alamos National Laboratory, reportedly discussing a recent surge of popular reports about unidentified flying objects. When the conversation turned to the broader question of extraterrestrial civilizations, at some point, Fermi is said to have posed a deceptively simple question to the table. Given the sheer number of stars in the galaxy, and given the vast span of time the galaxy has existed, where is everybody? The underlying logic is straightforward enough to state plainly: our galaxy contains on the order of 100 to 400 billion stars and has existed for roughly 13 billion years. Several billion years longer than the Sun and Earth themselves have existed. If intelligent technological civilizations arise with any appreciable frequency at all, then even a very modest rate of interstellar expansion, using nothing more exotic than slow, sublight speed spacecraft, should in principle be enough for a single civilization to colonize an entire galaxy the size of ours within a few tens of millions of years, an almost negligible span of time compared to the galaxy's full 13 billion year history. Given enough time, in other words, some civilization somewhere should already have had ample opportunity to expand across the galaxy and become obvious. And yet, as far as our observations have been able to determine, no confirmed evidence of any such civilization, past or present, has ever been found. This tension between the seemingly high statistical likelihood of intelligent life and the total absence of any confirmed evidence for it is what has become known as the Fermi Paradox. A related and highly influential framework for thinking about this question emerged 11 years later, in 1961, when American astronomer Frank Drake, working at the National Radio Astronomy Observatory, formulated what has since become known as the Drake equation, a formal way of breaking down the overall probability of detecting a communicating extraterrestrial civilization into a series of individually more tractable factors. The equation multiplies together the average rate of star formation in the galaxy, the fraction of those stars that host planets, the average number of planets per star capable of supporting life, the fraction of those planets on which life actually arises, the fraction of life-bearing planets on which intelligent life eventually evolves, the fraction of intelligent civilizations that go on to develop detectable technology, and finally, crucially, the average length of time such a civilization continues to release detectable signals into space before either falling silent or ceasing to exist entirely. That final term in the Drake equation, the average detectable lifetime of a communicating civilization, is where the Escation Hypothesis makes its most direct and most useful contribution. Most historical discussions of the Drake equation have treated this final factor somewhat crudely, as a single, simple number representing how many years, on average, a civilization continues broadcasting or otherwise remaining detectable before it either goes extinct or, in more optimistic formulations, simply matures past the need to broadcast loudly at all. The Escation Hypothesis suggests this picture is likely too simplistic and proposes instead that a civilization's detectability probably does not remain constant throughout its entire technological lifespan. It likely rises sharply during specific, relatively brief periods of energetic or environmental disequilibrium, whether driven by rapid industrialization, large-scale megastructure construction, or internal conflict, and then either falls back down again as the civilization successfully stabilizes into a mature, sustainable, and correspondingly quieter state, or terminates entirely if the underlying disequilibrium instead proves fatal to the civilization itself. Detectability, in other words, is likely not a flat, constant quantity across a civilization's entire history, but instead a spiky, highly variable one with the vast majority of any given civilization's total detectability concentrated into a comparatively narrow window of instability somewhere within its overall developmental timeline. This refinement matters because it changes how we should think about search strategy in a very concrete way. If detectability were roughly constant throughout a civilization's lifespan, then a longer average civilizational lifespan would straightforwardly translate into a larger number of currently detectable civilizations at any given moment. Since more civilizations would statistically be somewhere within their broadcasting window at any one time, but if detectability instead spikes sharply during narrow, transient windows of instability, then what actually matters most for our search efforts is not so much the average total lifespan of civilizations in general, but specifically how frequently these narrow, high detectability instability windows occur across the overall galactic population of civilizations, and just as importantly, whether our search instruments and observing strategies are actually well suited to catching a signal that might only be detectable for a period measured in years, months, or in the most extreme cases like a deliberate nuclear detonation, mere minutes. No hypothesis of this kind should be accepted uncritically. And the Escation Hypothesis has several genuine weaknesses worth taking seriously, precisely because taking them seriously is what separates a scientifically useful idea from mere speculation. The first and perhaps most significant weakness concerns the assumption that disequilibrium signatures scale in detectability the same way that purely physical phenomena like starlight or explosive energy release do. The 3/2 power law, describing how detectability scales with luminosity, works cleanly for phenomena that radiate energy roughly uniformly in all directions, phenomena governed by straightforward, inverse, square law physics. But not every proposed techno-signature necessarily behaves this way. A narrow, tightly beamed radio transmission, deliberately aimed at a specific target star system, would not spread its energy uniformly across the sky the way a star's light does, and so it would not become dramatically more detectable across a larger volume of space in the same simple way an omnidirectional signal like a supernova's light would. Similarly, a subtle change in atmospheric chemistry, the kind that might result from industrial pollution on a distant exoplanet, requires an entirely different detection method, transit spectroscopy, which depends on the fortunate geometric alignment of that planet's orbit as seen from Earth, rather than simple brightness across a survey volume, and so it does not benefit from the same 3/2 power law scaling at all. The precise mathematics linking detectability to disequilibrium may therefore vary considerably depending on exactly what kind of signal is being considered, and the hypothesis is on much firmer ground when applied to broadly radiating signals than to narrowly targeted or geometrically constrained ones. A second weakness involves the underlying assumption that a meaningful fraction of technological civilizations actually pass through some kind of loud, unstable disequilibrium phase in the first place, rather than developing gradually and sustainably from the very beginning of their industrial history. This is, at its core, an empirical question about how technological development tends to unfold, and we currently have exactly one confirmed data point to draw on: human civilization's own historical trajectory, which has indeed involved a fairly messy, environmentally disruptive industrial expansion. But generalizing from a single confirmed example to draw conclusions about an entire hypothetical galactic population of civilizations is a genuinely precarious exercise, and it remains entirely possible that human civilization's particular developmental path, shaped by our own specific evolutionary history, resource distribution and geopolitical structure, is itself somewhat atypical rather than representative of some universal pattern that other, very differently evolved civilizations elsewhere in the galaxy would necessarily be expected to follow as. Well, a third weakness concerns the timescale mismatch between astronomical detection windows and the length of time humanity has actually been capable of looking for these kinds of signals at all. The various astronomical detection biases discussed earlier, involving hot Jupiters, giant stars, and supernovae, have played out and been documented over an observational baseline stretching back centuries for some phenomena and at least many decades for others, giving astronomers ample opportunity to accumulate large statistical samples and correct for detection biases as instrumentation steadily improved over time. Systematic searches for extraterrestrial techno-signatures, by comparison, have really only been underway in any serious, sustained way since roughly the 1960s, and with genuinely broad, sensitive, well-funded coverage only in the past decade or two, it remains entirely possible that the current absence of any confirmed detection reflects nothing more than this comparatively short, observational baseline, rather than telling us anything meaningful yet about which category of civilization, loud and unstable or quiet and sustainable, is actually more common or more readily detectable across the galaxy as a whole. A fourth and more philosophical concern is the risk of anthropomorphizing alien civilizations too heavily, assuming that extraterrestrial societies would necessarily follow developmental patterns, energy consumption curves, and industrial trajectories that closely resemble humanity's own particular historical experience. An alien civilization built around a radically different biology, a radically different planetary environment, or a radically different social and political structure might industrialize in ways that produce entirely different disequilibrium signatures than the ones discussed here, or might avoid producing any significant disequilibrium signature at all, following a smoother, more gradual, less environmentally disruptive developmental path from the very outset, for reasons rooted in a biology or social structure fundamentally unlike our own. None of these weaknesses render the Escation Hypothesis useless or unworthy of serious consideration. Rather, they place it exactly where it belongs, as one plausible, scientifically grounded, but ultimately still speculative contribution to an extremely difficult and still largely unresolved question, deserving of genuine consideration and continued refinement, but not deserving of premature certainty in either direction. It is worth taking a closer look at the actual observational techniques astronomers currently have available for hunting down exactly the kind of disequilibrium signatures the Escation Hypothesis describes. Because the technology involved has advanced remarkably quickly over just the past several years, and understanding the methods helps clarify both what is realistically achievable today and what still lies frustratingly out of reach. The most mature and most productive technique currently in use is transit spectroscopy, a method that depends on a fortunate orbital alignment, an exoplanet whose orbit happens to carry it directly in front of its host star, as seen from Earth's vantage point. As the planet transits, a small fraction of the star's light passes through the thin ring of the planet's atmosphere on its way to our telescopes, rather than being blocked outright. Different atmospheric gases absorb light at very specific, well-characterized wavelengths, producing a distinctive pattern of dark absorption lines within the star's overall spectrum, a pattern that essentially amounts to a chemical fingerprint of whatever gases are present in the planet's atmosphere. The James Webb Space Telescope, launched in December of 2021 and now several years into full science operations, carries instruments specifically capable of capturing this kind of atmospheric spectrum with a level of sensitivity and precision that was simply not achievable with any previous space telescope. Webb has already successfully detected the presence of gases including carbon dioxide, water vapor, and sulfur dioxide in the atmospheres of several exoplanets, and mission scientists have identified a short list of nearby, particularly favorable target planets, most of them orbiting small, dim red dwarf stars where the atmospheric signal is easier to detect relative to the star's overall brightness, as prime candidates for more detailed follow-up observation in the years immediately ahead. The specific gases astronomers are most interested in searching for fall into two broad, somewhat overlapping categories. Biosignature gases are those whose presence in significant quantity would be difficult to explain through purely non-biological, geological processes and would instead suggest ongoing biological activity of some kind. Oxygen and methane occurring together in a planet's atmosphere being perhaps the most frequently cited example, since the two gases react with and destroy each other on relatively short geological timescales, meaning their continued joint presence in significant quantities would require some ongoing process, actively replenishing both simultaneously, a role that, on Earth, is filled by photosynthetic life continuously producing oxygen and various other biological and geological processes continuously producing methane. Technosignature gases, meanwhile, are those specifically associated with industrial activity rather than biology in general, certain synthetic chlorofluorocarbon compounds being a frequently cited example. Since these particular molecules have no known natural production pathway whatsoever and are produced, at least as far as we currently understand chemistry, exclusively through deliberate industrial synthesis. Detecting either category of gas in an exoplanet's atmosphere remains genuinely difficult with current instrumentation, and it is worth being honest about the scale of the challenge involved. The atmospheric signal from an Earth-sized rocky planet is extraordinarily faint relative to the overwhelming brightness of its host star, and confidently teasing out specific molecular signatures typically requires combining many repeated transit observations together over an extended observing campaign, sometimes stretched across a year or more of accumulated telescope time, simply to build up a signal strong enough to distinguish from background noise and instrumental artifacts. Even Webb, despite representing a dramatic leap forward in sensitivity compared to earlier space telescopes, is generally better suited to studying larger, warmer, more easily observed planets than it is to confidently characterizing the atmosphere of a small, cool, Earth-sized world orbiting at just the right distance from its star to potentially support liquid water on its surface. Complementing this space-based, spectroscopic approach are large ground-based and space-based radio and optical survey efforts specifically, searching for direct evidence of deliberate or incidental electromagnetic transmissions, rather than indirect atmospheric chemical clues. The Search for Extraterrestrial Intelligence Institute, founded in 1984 and commonly known simply as the SETI Institute, has coordinated numerous large-scale radio surveys over the decades, scanning across a wide range of radio frequencies for narrowband signals, meaning signals concentrated within an extremely narrow slice of the radio spectrum. Since natural astrophysical processes overwhelmingly tend to produce broadband emissions spread across a wide range of frequencies simultaneously, whereas a narrowband signal would represent a comparatively strong and specific indicator of artificial, deliberately engineered origin, the privately funded Breakthrough Listen initiative, mentioned earlier, represents the most extensive and best-funded radio search effort currently underway, utilizing some of the largest and most sensitive radio telescopes currently in operation around the world, and has systematically expanded its target list over the years from an initial focus on the nearest 1 million individual star systems to include entire nearby galaxies as well, casting an increasingly wide net in an effort to maximize the odds of catching precisely the kind of brief, non-repeating transient signal the Escation Hypothesis suggests would be our most statistically likely first detection. There is one more historical case worth walking through in detail, because it demonstrates something the earlier examples only hint at. Detection bias does not just distort which objects we happen to find first, it can actively distort our theoretical understanding of an entire field for years or even decades, until enough additional data accumulates to correct the picture. Before the era of large-scale systematic sky surveys, astronomers cataloguing distant galaxies faced a problem closely analogous to Malmquist's original observation about stars. A telescope of any given sensitivity can only detect galaxies above some minimum apparent brightness, and because brightness fades with distance. That limitation means any survey conducted out to a fixed, maximum observable distance will systematically miss the intrinsically faintest, lowest mass galaxies at the far edge of its observing range, while still comfortably detecting bright, massive galaxies across that entire range. The practical consequence is that early galaxy catalogues and the statistical conclusions astronomers drew from them regarding the typical mass, luminosity, and structure of galaxies throughout the universe were skewed systematically toward the brighter, more massive end of the actual underlying population, understating just how numerous smaller, fainter, lower mass galaxies actually are. It took decades of steadily improving telescope sensitivity along with the development of increasingly sophisticated statistical correction techniques specifically designed to account for this kind of selection effect. Before astronomers could confidently reconstruct a more accurate picture of the true underlying distribution of galaxy sizes and luminosities throughout the observable universe, a closely related historical episode played out in the study of gravitational waves, ripples in the fabric of space-time itself, predicted by Albert Einstein's general theory of relativity back in 1916, but not directly detected until a full century later in September of 2015, when the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO, recorded the unmistakable signal produced by two black holes, each roughly 30 times the mass of the Sun, spiraling together and merging into a single, larger black hole over 1 billion light-years away. This was, by any measure, an extraordinarily rare and extraordinarily violent event, involving two exceptionally massive black holes on a collision course, releasing, in the final fractions of a second before merger, more power in gravitational waves alone than the combined light output of every star in the entire observable universe put together. However briefly, ordinary stellar mass black holes, of the kind more typically formed through the core collapse of individual massive stars, tend to be considerably smaller, generally in the range of 5 to 20 times the Sun's mass rather than 30, and pairs of black holes massive enough and positioned closely enough together to actually merge and produce a detectable gravitational wave signal within the finite operational lifetime of an instrument like LIGO represent a comparatively rare astrophysical occurrence. And yet, precisely because of the almost unimaginable violence and energy scale involved in such a merger, LIGO and its successor gravitational wave detectors have now confirmed dozens of similar black hole merger events within just the first decade of operation, once again illustrating the exact same underlying pattern, an intrinsically rare, extreme event made detectable specifically because of, rather than despite its extremity, quickly coming to dominate an entire emerging field of study almost as soon as sufficiently sensitive instrumentation became available to look for it at all. Each of these episodes, whether involving distant galaxies, colliding black holes, exploding stars, or migrating gas giant planets, teaches essentially the same underlying methodological lesson, one that experienced observational astronomers have learned, sometimes the hard way, to keep firmly in mind whenever interpreting any newly emerging class of astronomical data. Whatever gets discovered first is very rarely representative of the broader underlying population it belongs to. It typically takes years, and sometimes decades, of continued observation, improved instrumentation, and increasingly careful statistical correction before a field's early, biased first impressions give way to a more accurate, more representative picture of what is actually out there. There is no obvious reason to expect the search for extraterrestrial intelligence to be fundamentally exempt from this same well-established historical pattern, and every reason, given how consistently the pattern has held across every other major category of astronomical discovery so far, to expect it to apply here as well, whenever and if that first confirmed detection finally does arrive. Where does this leave us? It is worth being precise one final time about what has actually been established here and what still remains genuinely open: the detection bias pattern itself, the consistent tendency for rare, extreme, energetically loud outliers to dominate astronomical discovery over their far more numerous but far quieter, more typical counterparts, is not speculative in the slightest. It is extremely well documented, repeatedly confirmed across planets, stars, supernovae, gamma-ray bursts, fast radio bursts, quasars, distant galaxies and merging black holes, spanning multiple independent subfields of astronomy and multiple independent observational techniques. From optical imaging to radio astronomy to gravitational wave detection, what remains genuinely speculative and genuinely unresolved is the extension of that well-established pattern to a category of object we have, as of today, never actually confirmed the existence of at all: a technological civilization beyond Earth? Applying a well-tested pattern to an entirely unconfirmed category of phenomenon is inherently a more uncertain exercise than applying it within a category like exoplanets or supernovae, where we already have thousands of confirmed examples to work with and compare against. Several concrete developments over the next decade or two should help sharpen and potentially test key predictions embedded within this hypothesis. Continued operation and expansion of wide-field, high-cadence survey telescopes like the Vera-Rubin Observatory will steadily improve our collective ability to catch brief, anomalous, non-repeating transient events of exactly the kind this hypothesis predicts would be most likely to represent our first genuine evidence of another civilization. Whether or not any of those events ultimately turn out to have anything to do with extraterrestrial intelligence at all, rather than some purely natural astrophysical process we simply have not fully characterized yet, continued improvements in exoplanet atmospheric spectroscopy, building on the foundational work already accomplished by the James Webb Space Telescope and extending into future planned missions specifically designed with direct exoplanet imaging and atmospheric characterization as a primary scientific goal, should steadily expand the number of nearby, potentially habitable worlds whose atmospheric chemistry can be characterized in enough detail to search meaningfully for both biosignature and technosignature gases, and continued expansion of radio and optical technosignature search efforts, building on the foundation laid by projects like Breakthrough Listen, should steadily improve both the total sky coverage and the total range of frequencies being systematically monitored for artificial signals. None of these ongoing efforts guarantee a detection, of course, and it remains entirely possible, perhaps even statistically likely given how comparatively short humanity's systematic search efforts have been so far relative to the immense age and size of the galaxy, that meaningful evidence either way remains decades or even centuries away, if it ever arrives at all. But each of these developments represents a genuine, incremental improvement in our collective ability to actually test hypotheses like this one empirically, rather than simply debating them in the abstract, and that alone marks meaningful, tangible scientific progress on one of the oldest and most profound questions humanity has ever asked itself. There is also a genuinely important asymmetry worth acknowledging directly, one that shapes how any eventual detection, should one ever occur, would likely need to be interpreted. A single confirmed detection of a loud, unstable, disequilibrium-driven technosignature would tell us relatively little on its own about the overall true frequency of quiet, stable, sustainable civilizations elsewhere in the galaxy, for exactly the same reason that a single detected supernova tells an astronomer relatively little about the overall true frequency of the vastly more numerous but far quieter, individually undetected stable stars scattered throughout that same galaxy, confirming or ruling out the presence of a larger, quieter population of sustainable civilizations, the kind implied by the sustainability solution discussed earlier, would likely require an entirely different and considerably more difficult observational approach, not broad, sensitive transient surveys scanning for brief flashes of anomalous activity, but instead extraordinarily precise, painstaking, individually targeted studies of the very nearest, most thoroughly characterized exoplanets conducted over extended timescales, searching specifically for the kind of extremely subtle, low-level but persistently anomalous signatures that a mature, highly efficient, low-waste civilization might still, despite its very best engineering efforts, be unable to eliminate completely. This underscores an important and often underappreciated point about the search for extraterrestrial intelligence as a scientific field more broadly. It is not, and realistically cannot be, a single unified search strategy applied uniformly across the sky. It instead requires a deliberately diversified portfolio of complementary approaches, broad, transient surveys optimized for catching brief, loud, unstable signals alongside narrow, painstaking, individually targeted studies optimized for detecting subtle, persistent low-level signals from the quietest, most mature and potentially most numerous civilizations that might otherwise never register in a broad survey at all. Neither approach alone is sufficient to give humanity a complete, unbiased picture of what might actually be out there, in exactly the same way that neither naked-eye observation of the night sky nor a targeted, narrow radial velocity survey alone was ever going to give early exoplanet astronomers an accurate, unbiased picture of the true underlying population of planets scattered throughout the galaxy. It took the combination of many different observational techniques, applied patiently over many years, each correcting for the specific biases inherent in the others, to finally arrive at today's far more complete and far more accurate understanding of how common planets, of every size and every orbital configuration, genuinely are throughout the Milky Way. There is good reason to expect that untangling the true nature and true prevalence of intelligent life elsewhere in the galaxy, whether loud and unstable, quiet and sustainable, or, quite possibly, some mixture of both existing simultaneously in different proportions at different stages of civilizational development, will require exactly that same patient, methodologically diverse, multi-decade approach. In the meantime, there is something genuinely valuable in simply having a clearer, more historically grounded framework for thinking about what kind of signal humanity is actually most likely to encounter first. Whenever that moment eventually arrives, if it ever does, it reframes the entire search for extraterrestrial intelligence away from the two dominant narratives popular culture has offered us for decades, either a hostile invasion force arriving with malicious intent, or a benevolent, wisdom-bestowing civilization arriving to guide humanity towards some kind of peaceful cosmic community, and toward a third possibility that is considerably less dramatic in the conventional sense, but arguably far more scientifically grounded, and in its own way far more emotionally resonant. Under this framework, first contact would not necessarily be an encounter with either an aggressor or a benefactor. It could instead turn out to be something closer to bearing quiet witness from an immense and safe distance to a civilization somewhere else in the galaxy passing through its own version of exactly the same turbulent, uncertain, high-stakes developmental period that human civilization is currently living through right now, on Earth, in real time, with the ultimate outcome of that period still very much undetermined. If that scenario does turn out to be broadly accurate, then the search for extraterrestrial intelligence becomes something considerably more personally meaningful than a purely abstract scientific curiosity about whether or not humanity is alone in the universe. It becomes, in a very real sense, an opportunity for self-reflection on a genuinely cosmic scale, a chance to study from a position of complete safety how another civilization somewhere else in the galaxy either successfully navigated its own period of rapid technological growth and energetic upheaval and settled into a long, stable, sustainable future, or alternatively, failed to navigate that same transition successfully and paid the ultimate price for that failure. Either outcome would carry profound and directly relevant lessons for humanity's own uncertain path forward, offered to us, quite possibly, from many thousands of light years away, and, depending on how far that hypothetical signal actually had to travel to reach us, from a civilization that met its own particular fate long before human civilization itself had even fully emerged. For now, the honest and appropriately humble answer to the question posed at the very beginning of this discussion, what would first contact with an alien civilization most plausibly actually look like, remains genuinely uncertain and will likely stay that way for a good while longer. But the history of astronomical discovery offers a consistent, well-tested and admittedly somewhat unsettling clue, one worth taking seriously precisely because it has proven so reliable across so many entirely unrelated categories of astronomical phenomena. Again and again for well over a century of careful observation, the quiet, well-behaved, Sustainable majority tends to stay hidden. It is the loud, unstable, temporary outliers that get noticed first, whether we are talking about planets, stars, exploding supernovae, or, quite possibly, one day, an entire civilization. If this way of thinking about the search for intelligent life resonated with you, it is worth carrying forward the next time this topic comes up in conversation, in the news, or in whatever future headline eventually announces humanity's first confirmed techno-signature, whenever that day finally arrives. And if you found this exploration of detection bias, disequilibrium, and the search for extraterrestrial intelligence genuinely interesting, sharing it, discussing it, and continuing to follow how these ongoing survey efforts and observational campaigns develop over the coming years is exactly the kind of engagement that helps keep serious, evidence-based science communication about these questions alive and reaching more curious minds. There remains a great deal we still do not know about our own civilization's ultimate trajectory, just as much as about any civilization that might exist elsewhere in the galaxy, and that irreducible uncertainty, rather than being a source of frustration, is precisely what makes this one of the most genuinely fascinating open questions in all of modern science, one that continued observation, continued technological improvement, and continued careful, patient reasoning will keep slowly illuminating, one data point, one survey, and one improved telescope at a time, for many years still to come.